In this video, I'm going to take a look at graphing systems of inequalities. This ties back into what we were just working on in the last video, graphing inequalities. Now we're going to be taking more than one equation at the exact same time, but we're going to be doing the exact same thing. We're going to be graphing the original boundary curve, boundary line, shading the region accordingly. So now we have multiple equations to kind of keep track of. So let's take a system, let's graph y is less than negative 1/2 x plus 3, and y is greater than equal to 2x plus 1. So we have two y values given to us here. We need to start by graphing both of these lines. Notice in the last video I didn't do any of these. I'll throw a few of them into this video. Sometimes things won't be given in the proper form to graph. If we have a line, we need y is equal to. If we have a quadratic, an exponential, a logarithmic, y is equal to. If we have a circle, it needs to be in that standard form. So make sure that the equation is in the proper form to graph. So I'm going to start with the first equation, and for illustrative purposes, I'm going to put that one in blue. So negative 1/2 x plus 3, our y-intercept there is 3. Our slope is negative 1/2, so that's down 1 to the right by 2. And that line should be a dotted line because we don't have the equal to bar on it. The second line I'll put in green, just again for illustrative purposes. My y-intercept is 1, my slope is 2, so I'm going up 2 over 1. And that one will be solid because we have the equals to bar now. Last video with inequalities, we talked about these test values. We can simply plug in a bunch of test values to test out which ones work. And that same strategy will work. So if I just want to kind of go plugging in values and testing, that will work. I'll do this first one using that technique, and then I'll take that intuitive approach. However, nice with test values, we have now 1, 2, 3, 4 different regions to have to check. So it's going to be a little bit more work than it was before. Let me start by testing something maybe in this upper region right here. So a test value that might work here would be, let's say, 0.5, definitely in that upper portion. 0.5 would be right up here. If we plug the 0.5 in, I'm not going to write it down, but we'll do it kind of talking it out. Is 5 less than 0 plus 3? Is 5 less than 3? No, it's not. So that failed from the first equation. It's not going to work. This region here is not going to work. Doesn't even matter if it works in the second equation, it has to work in both inequalities. Just like with our systems of equations, what we're saying is what we get has to work in all the different equations. So 0.5 does not work. Let me choose something in this region next, because just because I know it doesn't work here doesn't mean it has to work in all the other spaces. It should only work in one. So we know this one doesn't work. Let's choose something over here. So maybe 4, I'm pretty confident. 4, 3, I'm very confident would be in that second region. Is 3 less than negative 2 plus 3 is 1? Is 3 less than 1? No, it's not. So that one fails the first equation again. We'll move along to the next. Something in this region. Well, the origin's a nice easy point. Falls into that region. So 0, 0. Is 0 less than 3? Yes, finally, this equation works out. But we've got to check in the second as well. Is 0 greater than 1? No, it's not. So now because I've eliminated all the other 3 regions, I know that this is going to be the one that has to work, or else we've made a huge mistake. So let me choose a point that would be in that region. So let's say negative 4, 0. That would be right about here. If we plug that in, is 0 less than, that would be a positive 2 plus 3. Is 0 less than 5? Yes, it is. And then 0, is 0 greater than negative 8 plus 1, negative 7? Yes, it is. So we have the correct region. So we can absolutely use the test values as we have done in the past. We can also take that intuitive approach by thinking about what is this curve or what is this line telling me. This first line is telling me we want our y values to be less than the line itself. So we want to be under this blue curve, all this space. But then on the green line, we want to be greater than that green line. That would be all of the space up here. So kind of show this again. The blue, all of this. The green, all of this. Where do those two things overlap? Well, exactly what we had shaded before, the region in black. And so I'm going to move away from the test values pretty quickly here because I just think it's much faster, more efficient to work out in other ways. Let's take the equation x squared plus y squared is less than 9. and then we'll take the equation x squared plus y is equal to 1. First equation, not solve for y, but that's fine because that's the equation of a circle. That circle has a center at 0, 0 and a radius of 3, so we can graph that one as it is. The second one, however, we've got to convert over to y equals format because that is a quadratic and we do need to have the y by itself. So to get y by itself, I'm going to subtract that x squared over. Y is equal to, I don't want an equal to, sorry, let me change that. Greater than equal to is what I'd wanted to write. Greater than equal to, otherwise it's a very boring system of inequalities. It's not. Y is greater than equal to 1 minus, subtract the x squared over 1 minus x squared. So now let's graph both of the curves. And I'm going to go ahead and just do all black on this one because the two shapes are so different. So the first one, circle, center 0, 0, radius of 3. And I shouldn't have drawn it solid. I should draw it dotted because we don't have that equal to bar. So typically when I'm in class or I do this on paper, I would just sit there and erase points to kind of make it a dotted or dashed line. But I need to go back and make this one a dotted line. So there's my circle. And if we think about what we're trying to shade here, what we're saying is we want to be less than the radius of 3. We want our xy values to be less than that 9, so we want to be less than the radius of 3. So I want to shade inside. And a lot of times, especially as I get more and more equations, I make myself these little notes to remind myself where I want to shade. The second shape, y is greater than 1 minus x squared, or it's greater than equal to 1 minus x squared. This is a parabola with a shift up by 1 and a reflection about the x-axis, so it's now facing downwards. And this one should be solid, so it's going to look like this. We want our y values to be greater than this parabola, and so that would mean we want to graph the above. If we take those two ideas together, inside the circle, yet above the parabola, we would be looking at this space right here, a little crescent circle in a way. Not perfectly because it's following this parabolic shape, but still a portion of the circle. All right, let's take another example. Let's say we have y is less than equal to 3, x is greater than 1, but less than equal to 2, and we'll take the equation y is greater than equal to x cubed. With these systems of inequalities, we can take as many equations as we want. So here we have really four different curves or lines that are going to be drawn because this is really two kind of tied up in one. So let's look at how we're going to do this. Y is equal to 3 is a horizontal line, would be solid, would be right here. We want to be below this. So only things I can graph right now are below. The next one, x is between 1 and 2. Let me spread that out a little bit more. 1 and 2. 1 would be a dotted line. 2 would be a solid line. So right now I want to be in between these two vertical lines, but also less than, so I'm dealing with this infinite rectangle going downwards. I also want my y value to be greater than or equal to x cubed. So x cubed, remember, looks like this. And we want to be above that as well. So between the two vertical bars, below the one horizontal bar and above this, we're dealing with this semi-triangular, not really triangular, but this pie-like region right in here. I didn't mean to cross over the curve. So right in there, that tiny little shape. We can have as many equations as might be. Let's do one last example. Let's say we have y is greater than 3x plus 2, and y is less than 3x minus 5. Now right away something obvious should be jumping off the paper at us, which is to say these are parallel lines, but they're not the same line because they have different y-intercepts. The first one has a y-intercept at 2. It's going to be a dotted line. Looks going to look like that. Second one, y-intercept at -5. Still a slope of 3. 1, 2, 3 over 1. So again, parallel, should look parallel. And so if we think about what these are saying, the first one we want to be greater than this line, so we want everything up here. The second one we want to be less than this line, so everything down here. And let me kind of draw this out as two different colors. So again, the first one's saying all the green space. The second one's saying all the red space. Where do those two things overlap? Well, never. Therefore, there's no solutions to this. This is the empty set to know that 0 with a cross through it. There's nowhere where these two things overlap, and so really, we have nothing. There's no solution to this. So it's absolutely possible, not just for lines, but any shape, that their regions might not actually overlap, in which case we do get no solutions.